Welcome to my YouTube channel of the subject Basic Electrical Engineering. And in today's video, we are starting a new chapter that is a transformer. So before starting a chapter transformer, we must need to understand material used for the construction of transformer. So magnetic materials are used to construct a transformer's core. So basically in today's video, we are going to study about magnetic materials, different characteristics of magnetic materials, and lastly we will see BH curve, which is also known as the hysteresis loop. So let's begin with some important definition related to magnetic material. So the first definition is the magnet. What do you mean by magnet? So any material which is attracting iron particles or iron materials is known as a magnet. So we can say that any object that attracts the iron and which when freely suspended then it points toward Earth's magnet. So this is known as a magnet. Second is the magnetism. So the magnetism means the power by which magnet attracts the substances is known as the magnetism. Another two definitions related to magnetism are the magnetic materials. So the magnetic materials are the substances or materials which are attracted by magnet are known as the magnetic materials. Any magnet will exist as dipole. No magnet is available in a single pole manner. So when a magnet is freely suspended, so the end which point towards Earth's north side is known as the north pole of that magnet. And the magnet which point towards the south side of the magnet is known as the south pole. So in this way, any magnet is having the two poles that are the north pole and the south. So this was all definition related to any magnetic material. Now let's see some another definition and that are the permeability. So permeability is the most important one related to magnetic materials. So let's see what is the permeability. So all materials do not allow the magnetic flux to be produced through them. Some material allows maximum value of the flux can pass through them and some material does not allow even minimum flux can produce or pass through them. So iron, steel allows the magnetic flux to be produced through them very easily. So this property of material for the production or the flow of the magnetic flux to be produced through them is known as the permeability. So the material which allows more production of flux is having more permeability and the material which does not allow is having the less permeability. Air or vacuum has the poorest permeability. The permeability of air is given by this formula mu 0 is equals to 4 pi into 10 raised to minus 7 Henry per meter. Next definition is the relative permeability. We know the permeability of air. Now we can relate this permeability with any type of magnetic or any type of material is given. So that term is known as the relative permeability. So when permeability of any material is compared with the air, it shows the permeability of the material is how many times of that air, and this is known as the relative permeability. And relative permeability is having equation as mu r is equals to mu upon mu z. So if you know the relative permeability of any material and if you know the permeability of air, then you can easily find the absolute permeability of that material. So this was all about the permeability. Next is the types of magnetic materials. So there are so many types of magnetic materials available, but here we are discussing the major two types of magnetic material. So the first type of magnetic material is the ferromagnetic material. This is the very important magnetic materials in any type of electric machine. So the material whose relative permeability is very high, and relative permeability is very high, that means it has very high chances of production of magnetic flux through it. So relative permeability range between 100 to 1 lakh. So this material is known as the ferromagnetic material, and the examples are iron, steel, nickel, cobalt, etc. Such materials are used to make strong magnets. So they are known as the ferromagnetic material. Next magnetic material is the paramagnetic material, and this is the poorest form of magnetic material. So the materials having relative permeability between 1 to 10 or equal to 1 or slightly more than 1 are known as the paramagnetic material. An example of this kind of magnetic materials are platinum, manganese, aluminum, etc. So these materials are attracted by magnet but not strong. So mostly we are using the ferromagnetic material. So this was all about the types of magnetic material. So now our next concept is we need to find the BH curve or the hysteresis law. But before starting with this hysteresis law, you must need to understand what is B and what is H. So B is nothing but the magnetic flux density, and H is nothing but the magnetic field intensity, or you can say that magnetic force. So let's see how we can define the magnetic flux density. So the flux density B produced in any magnetic material is directly proportional to the magnetizing force applied to that magnetic material. That means if we apply more magnetizing force, then there will be more magnetic flux will be produced in per unit area. So we can say that high magnetic flux density. And if you apply small force, then it will be small. So the greater the H, the greater will be the magnetic flux density produced in material. So we can say that B is proportional to H. And just related to this fact, we need to draw the BH curve. So B is proportional to H, or you can say B divided by H is equals to some constant, and then constant is nothing but mu, where mu is known as the permeability. So B is equals to mu H, where mu is equals to mu 0 mu r into H in any type of medium. If you have different type of medium, then mu r will be different. And if you have a air as a medium, then mu r will be equals to 1. So this is the relationship between B and H. Now we need to draw a graph between B and H. So let's say that the BH curve's definition is the relationship between magnetic field strength, or you can say magnetic force H, and the flux density B for the particular magnetic material drawn on the graph for complete one cycle is known as the hysteresis loop, hysteresis curve, or you can say that BH curve. So ultimately we have to draw B versus H diagram. So to draw the B versus H diagram, consider this as a magnetic material. So with this magnetic material, we have to wound one coil over that magnetic material. So you can see in this diagram, we have wound some coil on this magnetic material. And this winding is given to some AC source of energy. You can see here, this terminals of this winding is given to the AC source. There is one switch and there is one resistance. Resistance is a variable resistance which is used to increase or decrease the current flowing through this winding. Because if we are increasing the current flowing through this coil or a solenoid, then the magnetic flux produced will be more. If we decrease the current, then flux produced will be decreased. So that's why we have connected one variable resistor to this diagram. So whenever we are connecting this switch, if this switch is closed, then some current will start flowing through this coil. And if alternating current is passed through any electromagnet, then magnetic flux will be produced in this magnetic material. You can see this red lines which represents a magnetic field. So this line are of magnetic flux. So now we need to find the graph of B versus H over one complete cycle. So if you want to find the graph of B versus H over one complete cycle, then here we are taking one waveform of current, because we will take current as a reference and we will draw B versus H graph. Means what if current is 0, what is the value of B and what is the value of H? If current is increasing, then what is the effect on B and H? If current is decreasing, if current has changed its direction. So we will take one current versus time graph here. So you can see that on x-axis we have taken magnetic field strength, or you can say magnetizing force H, and on y-axis we have taken flux density B. So now we have to draw the graph of B versus H. So let's say that at 0 point at origin, if no current was flowing, then B is 0 and H is also 0. But now as our switch is closed and current is started flowing in this electromagnet or in this solenoid, then we can say that current is increasing. And if current is increasing, so we can say that the magnetizing force is increasing. And if magnetizing force is increasing, then magnetic flux will start establishing in this solenoid. So we can say that at some moment of time, this B versus H graph is linear, and after some moment, this graph is curved. So it is not directly increasing, but it is slightly increasing with respect to H. Now, if current is reaching its maximum value, then no further increment in flux will be there. So we can say that this point is nothing but the saturation point of our BH curve. Because again and again, if we are increasing this current, then no increment of flux will be there. So this point is known as the saturation. Now, after reaching the maximum value of current, now current is decreasing. So if current is decreasing, then this magnetizing force will decrease, and if magnetizing force is decreased, then flux should decrease. So flux density will decrease. So you can see this graph. Flux density is decreased about D to E point. But you can see that here E point means zero current. And zero current means no current is flowing through this circuit for this moment. If no current is flowing through this circuit, then no flux should be generated and no flux should be present in this solenoid. But still, you can see that at zero magnetizing force, some amount of flux is present in this solenoid or in this coil. And this is nothing but due to residual flux, residual magnetism property of any magnetic material to store the magnetic flux inside it. So this is known as the residual flux, and this effect is known as the retentivity. Now, if we are talking about the reverse direction of current, means if now our current is reversed. Why we want to reverse the current? Because if you want to remove this residual flux, then what you have to do is you have to apply the magnetic flux in reverse direction. So that will be cancelled out, and now zero flux will be out. So if current is increased in the reverse direction, then this magnetic flux will be increased in the reverse direction. You can see that this magnetic flux is decreased about the reverse direction because first of all there was some residual flux, so we are giving the magnetizing force in the opposite direction, so there will be production of magnetic flux. But this magnetic flux right now is available only to cancel this residual flux. So up to this E to F point, no magnetic flux is there, but this flux is only required to cancel out the residual flux. So the magnetizing force which is given to cancel out this residual magnetism is known as the coercive force. So this force, magnetic force, which is given to nullify the effect of residual magnetism is known as the coercive force. So now once our coil is again having the current, increasing the current in the reverse direction, then we can say that now magnetic flux or magnetic flux density will be increased in the negative direction. So this E to F point was to about the cancel this residual magnetism, but after this F point the magnetic flux will be produced in the reverse direction like F to G. But at G point, our magnetic flux is now constant because this point is again known as the saturation point because maximum current has been reached at this point. So if now we are decreasing the current because in any alternating cycle after reaching its maximum value, now current will start decreasing. So the magnetic flux produced in the reverse direction of this magnet will start decreasing also. So you can see this point, this G2I point is decreasing magnetic flux, or you can say that magnetic flux density. So it is decreased at G2I. You can see that this GO2I, this O2I point is again known as the residual magnetism, because if our electric current is zero, but our magnetic flux density is not zero, that means it has stored some amount of energy in it. Again, if you want to cancel this O2I residual magnetism, then you have to apply the current again in the positive direction. So if you apply the current in positive direction, then the magnetic field will start increasing in the opposite direction to this. But this I to J magnetic field density is only used to nullify the effect of residual magnetism. And again, if current increased in the positive direction, then the graph will continue from J to D. So we can say that this graph will rotated in outer side of this magnetic curve. So in this way, BH curve can be drawn. This full graph is known as the BH curve. Now let's consider this figure, and in this figure, let's define all the terms. So the value at OC, the value OC means the retentivity or the radiance of the material, and it is known as the radiant or the residual flux density Dr. To demagnetize the iron bar, we have to apply the magnetizing force in the reverse direction. When H is reversed, by reversing the current flowing through the solenoid, because here we have given the DC supply. So in case of DC supply, you have to reverse the polarity of the battery. So the B is reduced to 0 at point D, and this is OD, and this OD is known as the coercive force. So the value of H required to wipe out the residual magnetism is known as the coercive force. So the measure of coercitivity of material. If after the magnetism has been reduced to 0, value of H is further increased in the negative or the reverse direction. So the iron bar again reaches a state of magnetic saturation represented by this point N. So this was all about the BH curve and types of magnetic material. So thanks for watching this video. Stay tuned.